It's a pleasure for me to be here. Thanks, Cultiva, for inviting me. And I'm going to show you and share with you some of the work we've been doing during the last years in the physiological and morphological factors that influence softening and dehydration in blueberries. I'm not going to talk into the cuticle right away. You'll have to wait a little bit for that, because I need to show you some aspects of this particular species, that's blueberries. Blueberries are fruits that ripen in a very sequentially mode, so you can find different kind of ripe fruit in different moments. And since the harvest index is just color, it's really hard to know how uniform a commercial unit will be. Those are the clamshells we sell to the markets. So we have been looking at and making this question, how uniform the fruit within a clamshell can be at harvest. And most important than that is what happens when the fruit reaches the final markets. For us, as an exporting country, our main defects of blueberries exported by Chile in the final markets are dehydration and soft fruit, the two topics that were listed in the titles and that will lead us to the cuticle stuff we are dealing with. And as I told you, in blueberries we have an asynchronous flowering and fruit ripening, both at clusters and at the whole plant level. But that makes that berries will develop under different environmental conditions. So within a single moment, like the picture you have on the top, you can find both flowers that are still opening and fruits that are already set. The ripening varies within a same cluster between the shade and the exposed side of the cluster. The picture in the white shows the same cluster looking a picture that has been taken from the shaded side and the same cluster taken from the sunny side. So at harvest, it is difficult to distinguish between ripe and overripe fruit. They all look blue, but you don't know which of them are ripe or overripe. And that leads, to a high variability in softening and dehydration. So, as it has been told this morning, the softening and the dehydration in all species, but also in blueberries, is affected by what we called an interaction between genotype, environment, and the cultural managements. So I need to talk to you about a little bit about all this before we go into the cuticle and what is important about that. Within fruit characteristics, I'm going to start talking about cultivars. And since the firmness is one of the most important issues that can be part of what the final market is looking for. They want firm fruit that can taste good. We have a lot of instruments to measure firmness, but the ones I'm going to show you now today are done with the FirmTech tool, which is the most precise one. The other ones that are listed in there are used by the industry because they are cheaper and they can be used in a much massive way. But I'm going to show you data on the FirmTech, which is much more precise. And the other thing I'm going to show you is how do we evaluate dehydration. It can be as percentage water loss or the amount of water that's that's lost by a surface or by time, and also the physical aspects that show dehydrated fruit. So starting with genotypes, the fruit characteristics, I'm going to talk first about cultivars, and within that, especially about firmness. The firmness at harvest as a function of release year has shown that until the 80s, the new varieties that were released had like a medium firmness that was not a trait that was important, but from then on, firmness has increased a lot. So every time a new cultivar is released, you wish it has a high firmness. But that's firmness at harvest. So what happens with firmness in post-harvest? What we look for is to varieties that will have low tendency to softening and low tendency to water loss. And when the breeding programs release varieties, they mainly focus on what the characteristics are on the fruit at harvest. For us, it's really important because we have a long-term journey with our fruit, sending it to Europe, even in the US. So for us, blueberries have to last at least 45 days or even more. And within this particular species, when we talk about a mean value for firmness, is not really a good indicator. If I show you this table that we're looking at a cultivar Brigitta that has a mean value of firmness at harvest of, was too fast. Of 250, and then after storage, it goes to 198. That is showing just a part of the frequency distribution of all that fruit. That is a frequency distribution of a commercial clamshell at harvest in black and in post-harvest in blue. So the mean value is representing just a small fraction of all those fruits. We have a big variation. The coefficient of variation can increase from 14% to 33% after storage. And we don't care about the fruit that's firmer than the mean, but what happens with all that fruit that's less firm than the mean, and that's very important. If we compare blueberries to apples, we have the same exercise. We have a mean at harvest that shows 18 pounds. After 90 days of storage, it falls to 16.3, but the coefficient of variation is no longer than 6.5. So in that kind of crop, the mean value would be a good, would represent the whole bunch of fruit in a good way, not in blueberries. Okay, and the thing is that we've seen that this is common to any genotype, even if you can classify them in low, medium, or high firmness at harvest. They all show this tendency to have a higher amount of soft fruit that is really dangerous for the process after storage. The new genotypes, of course, are trying to deal with releasing cultivars with higher firmness. This is a bunch of genotypes we are evaluating at the university, and we have this red cultivar as like our control, which is Duke for us, and all the other ones that have at least a mean that is higher than 200 grams per millimeter, which is a very good firmness for the fruit. Okay, and also these new genotypes are having lower percentage of soft fruit. You can see that a bunch of them have less than 5% of soft fruit, but this is at harvest. So we still need to know what will happen with them at post-harvest. But again, in this other one, you can see that variability still remains. I mean, the black dots are the means, and the other one, the lines are the standard deviations for those means. So, before I enter in the cuticle, the waxes, and the scars, let's see how the fruit interacts with the environment. The optimum conditions for growing blueberries is around 15 to 25 degrees Celsius. That would be like 68 to 80 Fahrenheit, I guess, and hopefully no precipitations. What we are seeing nowadays with the climatic changes is that that's not happening, and we are having fruit that is exposed to much higher temperatures and rains during periods that we were not used to have them. And the other thing is that different cultivars will have a different ripening period. So depending if they are a short window harvest or a long window harvest, they will be exposed to different conditions. Most of my presentation will be done in Duke and Brigitta, which are two very different cultivars. They are different because one is a short window harvest and the other one is a long window harvest, but they have very different post-harvest behavior. So for us, it's like we use those two to make contrast and see how the differences can be expressed. In here you see that we have the ripening period of the two of the cultivars, and the green line shows the minimum temperatures and the orange line the maximum temperatures. So you see that Brigitta is exposed to a much more variable condition and increasing temperatures as the summer goes on. So asynchrony during ripening will have a different impact depending on the proportion of fruit that is on each development stage at the time that a high temperature or a rain occurs. We have, on blueberries, we have to go harvesting fruit every 3 or 6 days to get the mature fruit that's inside, that's ready to get harvested. And here we have the difference we can see for the two cultivars during two seasons. If you see the first season is the blue one, it was cooler and with less rain, so the frequency distribution of firmness is shifted to the right, higher firmness and a steeper distribution. And the second season, with higher temperatures and rains, shifts the frequency distribution to the left, so we have more soft fruit. So the same cultivar can behave very different during two different seasons. The same fruit, we measured the amount of soft fruit. This is the distribution of the firmness. Instead of a frequency distribution, we are looking here at box and whisker plots. And the red line is in the what we call the soft fruit firmness. And you can see that within the second season, the one that was warmer, we had like 42% soft fruit in Brigitta and 25 in Duke. And in the previous season, which was cooler and with no rains, the percentage were 5 and 10 respectively. So it's really different the way the fruit responds to the environment. Given cultivar will respond differently every year depending on the season and the environmental conditions. This is a recent paper that shows kind of the same firmness measurements of different genotypes that are classified as firm, like higher than 240 grams per millimeter, medium or low firmness. And if we look at one in particular, Susie Blue is one of the genotypes we are using in Chile, and has a lot of years being evaluated. And you can see that if that's the target firmness, during different years, you get very different values as mean values. The same happens with the medium fruit and with the low firmness fruit. So again, the year leads to a very different behavior of the fruit. And the third component is all the cultural managements we are making, and especially I'm going to talk about harvest and post-harvest. If we are harvesting blueberries in the morning and we measure the temperature of the air, which is this blue line, and we measure the temperature of the fruit that's growing at the shade, they follow mainly the same line. But the fruit that is growing at the sunny side of the plant can be like 10 degrees higher in temperature. And we're putting all those fruits in the same clamshell. So that's part of the high variability we are looking when we're harvesting fruit. This is a very simple experiment. We made harvest in the morning with lower temperatures and in the afternoon with more than 30 degrees Celsius. And for different harvests, first, second, and third harvest, remember this fruit is harvested in a lot of moments. And we might not see much of a difference between the AM and PM fruit at harvest, but then in post-harvest, all the fruit that was harvested in the afternoon tend to shift their frequency distributions to the left. So what was not seen at harvest was seen in post-harvest, and fruit that was harvested in the afternoon show lower firmness at post-harvest. How can we deal with all these factors? We took fruit from different firmness that were segregated as soft, medium, or firmness, and we looked at how they behaved during 2 years. This is Duke, for 35 days at 0 degrees Celsius. So you see that all of them, they start with a certain firmness, and they show a slope of decreasing firmness. And compared to Brigitta, there's a really high difference. In Brigitta, we have fruit that starts with a lower firmness than in Duke, but the tendency across the time is that the firmness will not drop as dramatically as it does in Duke. So that's what we need to know why. As I told you at the beginning, the visual differences between ripe and overripe fruit are not evident at harvest, but they become more pronounced when the fruit is set under storage, and this is what happens after 40 days at 0 degrees. We have ripe and overripe fruit, and you see that there's differences in firmness, in water loss, in sound fruit, both for Duke and Bridita, but these differences are highly greater when a management is used. The use or to use or not to use bags as a modified atmosphere packaging makes a really high difference. And here you see that by using, by not using the bag in Duke, we had a reduction in 34% of firmness, an increase of 66% of water loss, and a 69% decrease in percentage of sound fruit. The same measurements for Bridita, the one that went less, that had a less drop in firmness, was 12, 48, and 12%. So there is a difference between the cultivars that we need to manage. And that took us to the question that why measuring firmness at harvest is not enough to estimate post-harvest firmness. As in many other species, like I was telling you on apples, if you have a firmness at harvest, you can predict what the firmness will be in post-harvest. For blueberries, that doesn't work. You measure firmness at harvest and you measure firmness in post-harvest, and you don't get a very nice association like it's in here. But fortunately, like 10 years ago, Paniagua and other colleagues found a really nice relationship between weight loss and firmness. And we started working with these two parameters to try to see what's happening in this crop. As it was said, here will come the softening and dehydration is highly related to the amount or the structure, the composition, and the content of waxes. But in the case of blueberries, not only the cuticle, that we call it as a bloom, is important, but also this is a fruit where a pedicel scar is present, and the size and permeability of that scar is also important. This is one of the few fruits where the fruit is detached from the pedicel when it's harvested, so that's a very important way for water release. So again, we started looking at what happens with these two varieties, what happens with the waxes, and along with firmness and dehydration, we started looking at cuticle permeability, when the bloom is removed, and scar permeability, or more than scar permeability, like a pore diffusivity, when the scar was sealed. And we started looking at the effect of scar and cuticle on water loss, like I said, in the first place, by sealing the scar so that we would allow the water move only through the cuticle. The fruit in the middle is the control that was not intervened, and the one in the other side is a fruit where bloom was removed. And when we looked at the rate of water loss, if you see the blue bars are the water loss that the control fruit is showing, and for the pink bars, where the scar was sealed, we had a decrease of 15 to 39% in firmness because the scar was preventing water loss from getting out from the fruit. And when the wax was removed, we had an increase in water loss from 23 to 53% depending on the cultivar. We were removing the cuticle, we were letting water out of the fruit. And we also found that there's a very high relationship between the stem scar diameter and the rate of water loss from the fruit. So the bigger the scar, you can expect a bigger water loss in the fruit. We were working with some genotypes from a particular breeding program we had, and we were able to estimate the water loss via scar and via cuticle, both at 0 and 20 degrees Celsius. And when we looked at the rate of water loss of cuticle to scar at room temperature, it was 9. I mean, the cuticle was much more important than the scar at room temperature. But at low temperature, that ratio went to 1.2. So the scar is getting an important role in the fruit water loss when the fruit is set at low temperature, which is how we store it. So at 0 degrees Celsius, the scar can account for up to 60% of the water loss in the fruit. And that's an important thing because we don't only need to be aware of the cuticle, we also need to be aware of the scar of each cultivar. Within the wax, there are some components of the waxes that are really present in higher amount. Triterpenes are the most important components on wax for many fruits, and especially for blueberries. And you can see amyrin, ursolic acid, orlenolic acid, and lupeol. The permeability of the fruit, and it was said this morning, doesn't relate with the amount of fruit, but more with the composition. Here we have those two cultivars we were looking at in different ripening stages. They have no difference in the amount of fruit at the time they were harvested. But they did have differences in water loss. So we looked at the components that were within the cuticle, and we found for the different maturity stages that especially oleanolic and ursolic acid were very important. Duke had a higher amount of ursolic acid and low amounts of oleanolic acid, and Brigitta had the opposite, a high amount of oleanolic acid and very low ursolic acid. And in terms, the first one is the one that had high water loss, and the other one had lower water loss. So we were able to look at and find some correlations between water loss and firmness loss, especially with ursolic acid, and in the case of oleanolic acid, a negative correlation with firmness loss. This work was done in 2017, and there has been a more recent work done by Jan and Castellarin that were looking at similar cultivars and also at the triterpenes. And you see that oleanolic and ursolic are the ones that are most abundant in all of them. But take a look at Duke, in which ursolic acid is higher than oleanolic. That makes it's similar to the results we found. And then when they were looking at the water loss rate, it was Duke the one that had the highest water loss rate related to this oleanolic and ursolic acid ratio. We made some experiments with these two cultivars in different maturity stages, trying to see what was explaining the differences between the cultivars. And through a principal component analysis, we were able to segregate Duke and Brigitta into two groups. And when we went to see which were the variables that were explaining those differences in terms of cultivars, the ursolic to oleonucleic acid arose as an important trait. This is not an easy way to, it's not easy to evaluate these components. So we're trying to do it a little easier. And we started looking at fruit behavior at different relative humidities. And again, you have Duke and Brigitta on the right and on the left and the right side. And how do they behave in water loss across 10 days at different relative humidities, from 30 to 96%. And you see at the end of the period that Duke shows a very different water loss even at high humidities. The ones that are circled in there are 84, 95, and 96. And for Duke, those are really much lower. So we can turn this information into what's in the graphs below. We have the water, we can express the water loss rate per day in terms of relative humidity. And we see that both cultivars have a really different pattern. I'm going to show you the same two graphs again in the next slide. So here we have Duke, here we have Brigitta. How does it looks in terms of rate of water loss related to relative humidity? And let's see how they behave now when we seal the scar or we remove the bloom. When we seal the scar, Duke is much more influenced than Brigitta, and when we remove the bloom also. So you see there's a much more influence both of the scar and the cuticle in Duke than in Brigitta, and we assume that this is in part the explanation of what I showed you previously, where the firmness loss in Duke was much steeper than the one in Brigitta. With this in mind, we started to try and develop a device that would help us study the fruit at an individual level. We were covered in Hort Science in 2023. And with this device that we developed, we wanted to assess the impact of these three elements: genotype, environmental, and management during fruit growth on the post-harvest behavior of the fruit. When we look at experiments at a clamshell level, the random arrangement of the fruit within that clamshell does not allow the expression of dehydration and softening. So we are introducing this simple device that can hang 5 individual fruits, and the main thing here is that we want to expose the fruit as much to we want to have a much exposure of the surface area of the fruit to the surrounding environment, including the scar. Because within the clamshell, if the fruits are touching, one scar is touching the fruit, that will make a different, it will give you a different response of what is happening with that fruit individually. So this is the system we came up with. We have an air pump where we obviously pump air into a glycerol with water solution, and that makes a different relative humidity that we pass through a sealed box. Within that sealed box, we can have whatever we want in terms of treatments. We can have the entire fruits, or we can paint the scars, or we can remove the bloom. And that's how it looks at the lab. We have different boxes. Each one has a different relative humidity. So by exposing those individual fruits to a gradient of relative humidity, we generate different vapor pressure deficits, and that difference in water potential between the fruit and the surrounding environment drives water vapor from the fruit and causes dehydration and softening. So what we do is we take these fruits, we put them in these devices, we hang them in a box, the box is sealed, and then it's subjected to different. We are using now 3 different relative humidities, and we wait the fruit for 10 days. The purpose is the higher the relative humidity will have a lower VPD, and so a lower water loss rate, and in the opposite, the lower relative humidity, which is about 30%, will have a higher VPD and a higher water loss rate. What we have seen with this is that the differences between ripe and overripe fruit can be enhanced and can become evident under low relative humidity. Here you have ripe and overripe fruit, the rate of water loss, and for the fruit that's at high relative humidity, no differences in water loss, but you can see them when you expose them to a lower humidity. And the relative contribution of the cuticle and the pedicel scar is also evident when you expose those fruits to different and low relative humidities. So again, the bars in blue are for the high relative humidities, but the ones in orange are the low relative humidity, and you can see that the differences are much more evident. So what we are proposing is that with this system, we can look at differences among cultivars, because genotypic traits related to the post-harvest potential become evident when the cultivar is exposed to adverse conditions. If we look at the cultivars at the high relative humidity, we see no differences. But when we expose them to a gradient of relative humidities, we can see that ones will behave better than the others. And this is what we've done. This is the last work we are doing with new genotypes, where we are plotting the rate of water loss against the rate of firmness loss for each of the relative humidities we are working with. And in general, you can see that the higher the water loss, the higher the firmness loss. But if we look at some specific genotypes, like this one, that's a not really good genotype that has high rate of water loss and high rate of firmness that increases when the relative humidity decreases. But look at this other one. That shows a very little movement in terms of rate of water loss and rate of firmness loss, regardless of the relative humidity we're using. So this could be a really nice way of kind of selecting which are the most resistant cultivars to adverse conditions, rather than having to measure the ursolic and or the oleanolic acid in every one of those. So what we're looking for in new cultivars is, okay, yeah, we will have a ranking for firmness at harvest, and those are rated like number 1, 2, 3, 4, and 5 in terms of firmness. But when we subject them to these differential relative humidities, the ranking changes. Now cultivar 3, that was rated on the second place at harvest, shows the highest potential for post-harvest because it has the lowest rate of water loss within this in this group. And cultivar 1, which was the highest in the firmness at harvest, goes into a third place with this system. As conclusion, asynchrony in flowering and ripening contributes to a high variability in firmness and quality, both at harvest and in post-harvest. The storage potential of blueberries is limited by their high sensitivity to this G by E by M during the growing season, and that leads to how the scar and the cuticles are formed. Firmness at harvest does not predict firmness at post-harvest. However, softening during storage is driven by water loss, so there can be a better correlation. The effects of this G by E by M on post-harvest potential can be estimated by exposing individual fruits to accelerated dehydration. These individual fruit assays under a gradient of relative humidities can allow the selection of new genotypes with greater shipping aptitude. I mean, if what we're looking at is cultivars that could stand even if there's a break in the cold chain during the post-harvest period. And future research is we need to do a deeper characterization of the pedestal scar. We need to assess the cuticle compositions of cultivars with constraining post-harvest behavior. And we aim to develop with this work a long-term post-harvest index that could be used for the selections of new cultivars, thinking not only in firmness at harvest, but how does the fruit behaves in post-harvest. Thank you for your attention, and I can take any questions now.